Hey guys, so in the last lecture we have understood the idea of inductive reasoning or basically mathematical induction. Now in today's video we will learn about the formal method to do a mathematical proof via induction, and we will also see some of the examples. But before that, notice that this method of proof will only be applicable once we are doing some generalized mathematical proofs which are dependent on natural numbers. So let's begin and understand this more clearly. But before that, let's note a rule of thumb. So this rule of thumb states that to prove that a statement is not true, it is sufficient to cite one particular case where the statement is false. For example, this is a statement. It says that n square by 2 is an even number for all natural number n. Well, intuitively we can feel that this is not a correct statement. But to prove that this is not true, we have to show one particular case where this statement does not hold. Well, put n is equal to 1. Then n square by 2 will be equal to 1 square by 2, which is equal to half. And half is not an even number. So this statement is false. Why? Because by our rule of thumb, we have shown here one particular case where the given statement is false. That is that n is equal to 1, n square by 2 is basically 1 square by 2, that is equal to half, and that is not an even number. So basically we have shown here one particular case where this statement does not hold. This means this given statement is not true in general. Now let's see the formal definition of the principle of mathematical induction. So the principle of mathematical induction says that suppose there is a given statement P of n where the statement depends on the natural number n, such that property number 1, this says that if the statement is true for n is equal to 1, that is P1 is true. Well, you all must be thinking that why we have checked the particular case just for n is equal to 1. Why not for 2, 3, 4 or so on? Well, we will come to this in the later part. Before that, let's read the property number 2. So this property says that if the statement is true for n is equal to k, where k is some natural number, then the statement is also true for n is equal to k plus 1. That is, the truth of pk implies the truth of pk plus 1. So if these two property holds, then we can say that Pn is true for all natural number n. Well, these two properties are important, and in order to, it means we have to first go for first property and then we have to go for second property. It means first we have to check for some particular cases. From there, by the rule of thumb, if the statement is false, there it will get rejected. It means there we can conclude that the given statement is not true, as by our rule of thumb, right? Now let's understand both of these properties one by one with the help of some examples. So let's start with the first property. So this property says that if the statement is true for n is equal to 1, that is P1 is true. Well, this means in this property we are checking the particular case, but we left that with a question that why n is equal to 1. Well, mathematically speaking, you can check it for n is equal to 2, 3, 4, 5, 6, 7 or any natural number. It's not going to make any difference. But why 1? Because to avoid cumbersome calculations. You know, like 1 is the least natural number and that make our calculations very easy. Now let's understand this property with the help of an example and understand why this property comes before the second property. So consider the example. This says that Pn is n square plus n is an odd number for all natural number n. Well, if we will keep n is equal to 1, we will get 1 square plus 1, that is equal to 2, and 2 is not an odd number. So from here itself, we can conclude that the given statement is not true in general and we don't have to go for the second property, right? But suppose the first property holds, that is P1 is true. Still we are getting the intuition that the given statement is not true. Then there the role of second property comes, which will help us to prove that the given statement is not true, or we can say the given statement is false. So let's consider an example to understand this. Consider the statement Pn that says that n square is equal to n for all natural number n. Well, by the first property, put n is equal to 1. We will get 1 square is equal to 1. This implies P1 is true. But we are getting the intuition that this can't be true for all natural number n, right? Like put n is equal to 2, we will get 2 square, and that is not equal to 2. So by here also we can say that this statement is false because we have provided one particular case where this statement does not hold. But let us suppose that we have assumed that property 1 is satisfying. Now we have to actually go to the second property to check that, right? So let's go to the second property and check whether this holds or not. And then we will understand the importance of this second property. So now by second property, let's assume that this is true for n is equal to k, where k is some natural number. So this implies that k square is equal to k, right? Now we have to prove that pk plus 1 is also true. That is, pk plus 1 shows that k plus 1 whole square is equal to k plus 1. If you are able to prove this, then our statement is true in general. So let's start with k plus 1 whole square. So k plus 1 whole square is equal to k square plus 2k plus 1. But by our assumption that pk is true, we can write k square is equal to k. So this implies that k plus 1 whole square is equal to 3k plus 1. That is not equal to k plus 1. So from here we can conclude that our given statement is not true in general. Now let's understand the importance of the second property. So the second property says that if the statement is true for n is equal to k, then the statement is also true for n is equal to k plus 1. That is, the truth of pk implies truth of pk plus 1. Well, what does that mean? It means that we are proving the result for all natural numbers. How? Because here we are assuming that the result is true for kth term, and then we are proving that it's going to be true for k plus 1 term. So if we are going to keep k is equal to 1, and then we are proving that it is true for k is equal to 2. If you are assuming that k is 2, then we are proving it for 3. If you are assuming that k is 4, then we are proving it for 5. And so on, we are going to cover all natural numbers. So hopefully you have understood that how this principle of mathematical induction works. Now let's consider some examples to understand this very clearly. So consider this question from the previous lecture which we promised to prove in this lecture. This is sum of first n natural numbers is equal to n times n plus 1 by 2 for all natural number n. So basically our Pn is this statement. Now let's check it for n is equal to 1. So for n is equal to 1, here it is 1. Now put that in formula, we will get 1 times 1 plus 1 by 2, and that is equal to 1. This implies that P1 is true. Now let's assume that the statement is true for n is equal to k. So this implies that 1 plus 2 plus 3 plus so on till k is equal to k times k plus 1 by 2. Now let's prove that for pk plus 1. So pk plus 1 is basically 1 plus 2 plus 3 plus 4 plus so on till k plus 1, and that has to be equal to k plus 1 times k plus 2 by 2. If you are able to prove this, then we can say that this statement is true in general. So let's consider this. So this is basically 1 plus 2 plus 3 plus 4 plus 5 plus so on till k plus 1. Now observe that this is nothing. This is sum of first k natural numbers, and by our assumption that pk is true, this is equal to k times k plus 1 by 2 plus k plus 1. If we'll solve this, we will get k plus 1 times k plus 2 by 2, and that is equal and as desired. So basically this implies that pk plus 1 is true when pk is true. So we can say that pn is true for all natural number n. Now let's move to the last example of the day. Read this question. This question is saying that for all natural number n, Pn is true, where Pn is 1 by 1 times 2 plus 1 by 2 times 3 plus 1 by 3 times 4 plus so on till plus 1 by n times n plus 1, and this is equal to n by n plus 1. So pause the video and try it yourself. I think most of you have done this right. So let's start this. So first put n is equal to 1 in this. So we will get 1 by 1 times 2, that is equal to half. Now put in the formula, that is 1 by 1 plus 1, that is also equal to half. So this implies that P1 is true. Now let's assume that Pk is true for some natural number k. So this implies that 1 by 1 times 2 plus 1 by 2 times 3 plus so on plus 1 by k times k plus 1 is equal to k by k plus 1. Now what will be Pk plus 1? Pk plus 1 will be 1 by 1 times 2 plus 1 by 2 times 3 plus so on plus 1 by k times k plus 1 plus 1 by k plus 1 times k plus 2, and this we need to prove that this is equal to k plus 1 by k plus 2. Now let's take the left hand side of the equation, that is 1 by 1 times 2 plus 1 by 2 times 3 plus 1 by 3 times 4 plus so on plus 1 by k times k plus 1 plus 1 by k plus 1 times k plus 2. Now observe that this is nothing but this is sum of first k terms, and by our assumption that pk is true, we'll get this is equal to k by k plus 1. So basically sum of this term will be equal to k by k plus 1 plus 1 by k plus 1 times k plus 2. Now after solving this, we get 1 upon k plus 1 times k square plus 2k plus 1 by k plus 2. And this we can write as k plus 1 whole square by k plus 2 times 1 upon k plus 1. Now we can cancel this. After this we will get k plus 1 by k plus 2, which is as desired. So this implies that pk plus 1 is true when pk is true. Hence we can conclude that pn is true for all natural number n. Now I am sure you all must have understood this new method of proof, which is the principle of mathematical induction. So we will meet in the next video to solve some different problems on this method. So let's summarize what we have learned today. Suppose there is a given statement Pn involving the natural number n such that the statement is true for n is equal to 1, that is P1 is true, and if the statement is true for n is equal to k, where k is some positive integer, then the statement is also true for n is equal to k plus 1. That is, truth of pk implies the truth of pk plus 1. Then Pn is true for all natural number n.